Most engineering teams shipping a multilingual tool-using agent test one thing. Did it get the answer right? We prompt the agent in Hindi, check the English baseline, verify they match, and ship it. But an identical text output can easily hide massive structural differences in how the model actually operates. This network map shows internal execution pathways. The English prompt triggers a direct, efficient sequence: search, compute, answer. The Hindi prompt sets off an erratic loop: translate, search, translate again, compute, and finally answer. Both paths return a passing grade at the final node, but that looping Hindi pathway burns 3 times the tokens and triples your execution latency. Furthermore, your tool permissions, rate limits, and audit trails are entirely written around the direct English sequence. They are functionally blind to the erratic operations executing on the non-English path. For a tool-using agent, the final text output is an illusion. The sequence of actions, the route itself, dictates your costs, your failure surface, and your compliance. The route is the product. To properly evaluate these agents, we have to stop scoring the final answer and start measuring the intermediate route. We call this sequence the action trace. A recent study tested this across 41 languages. To ensure a strict mathematical comparison, researchers forced all inputs through a shared, universal 5-tool symbolic alphabet: search, calc, translate, summarize, and finish. Crucially, these tools are strictly parsed and compared. They are never executed. This isolates the model's internal decision-making policy from external variables, like a web search altering the agent's state. Once the action traces are extracted, we use a normalized notching block formula to quantify their similarity. Similarity, S, equals 2 times the matching blocks, divided by the combined length of trace A and trace B. Apply this formula cleanly across languages, and the numbers you get back will be completely untrustworthy. Applying it directly to stochastic sequences introduces 5 severe mathematical confounds. Each confound alone is mathematically large enough to reverse a model's true performance ranking. Standard answer scoring evaluation suites are mathematically incapable of isolating the true language signal from raw sampling noise. To find the true cross-lingual gap, we must push the data through a rigorous 5-stage correction pipeline. The first block is C1, the identification failure. If you ask a stochastic model the exact same question twice in its own language, it will not perfectly reproduce its own action trace. Look at this chaotic data stream. Without a baseline, you're solving one equation with 2 unknowns, unable to separate language changes from raw sampling noise. The fix? Generate every cell twice, altering only the serving seed, establishing a matched replicate baseline to filter inherent noise. Applying this baseline immediately proves that unmatched data artificially suppresses the severity of the cross-lingual divergence. The properly matched estimate is nearly 40% larger than the raw, unmatched baseline. Any cross-lingual leaderboard failing to include a matched replicate baseline is measuring a mathematically unidentifiable quantity. Next is C2, length bias. Because the similarity equation intrinsically favors shorter sequences, removing a tool creates a false compression echo. Shorter traces mathematically masquerade as better policy retention. The mandatory correction is bilateral length matching. We only accept the estimate when length comparisons agree in both directions, pushing our pooled gap tracker up to 0.0878. The third filter, C3, addresses empty traces. Under the formula, if you compare 2 completely empty sequences, they automatically generate a perfect 1.0 similarity score. This mathematical quirk exposes a severe real-world anomaly involving the open-source model GPT-OSS-120B. On raw leaderboards, this model posted massive cross-lingual invariant scores despite registering under 2% accuracy. It achieved this because it produced an unparsable, empty trace on 76.4% of its rollouts. The model was not broken, the extraction parser was. The agent was answering in natural prose and explicitly naming the correct tools, but it failed to output the rigid syntax required by the regex extractor. Providing 2 worked exemplars directly repaired this regex artifact. The formatting intervention made the model legible to the parser, raising its measured accuracy 26-fold. If you rely on unaudited evaluation harnesses, rigid measurement extraction failures will routinely masquerade as deep structural model failures. The fourth filter handles C4, the reproducibility ceiling. The absolute gap between two traces is strictly bounded by a model's internal determinism. We shift to an identifiable estimand, a normalized ratio called I tilde. This chart shows model variance. At standard temperature, model identity drives 75% of variance, but switch to greedy decoding at t=0, and that variance collapses to just 5.7%. The apparent temperature dependence of the gap is an illusion caused by the reproducibility ceiling shifting down, rather than the true cross-lingual signal changing. The final filter is C5, the chance floor null. With a 5-tool alphabet, unrelated traces agree by chance over half the time, inflating scores for smaller models. Permutating the arrays establishes this exact chance floor, pushing our final pooled gap to plus 0.2074. Systematically stripping away these 5 layers of stochastic noise does not shrink the cross-lingual gap. It proves the gap is structurally robust, landing at a value 4 times larger than the raw baseline suggested. The core revelation of this pipeline is absolute. The measurement confounds were actively suppressing the severity of the language gap, not creating it. This chart displays policy retention across 4 radically different frontier architectures, ranging from dense models to massive mixtures of experts. As you can see, at greedy decoding, they all land exactly within a tight 71 to 73% policy retention band. Despite vast differences in training data and scale, these frontier models uniformly lose between 27 and 29% of their own action policy the moment the language changes. Below the 10 billion parameter threshold, this regularity breaks down entirely. The apparent rankings of smaller models are largely an artifact of the uncorrected chance floor. This uniform policy drop is an inherent structural property of frontier AI. It represents the true multilingual gap. We know the precise scale of this structural drop. The specific behavioral mechanism driving it is the English pivot. This node graph maps the English pivot. When handed a non-English task, these models aggressively resist direct execution. Instead, they forcibly route the data through a bottleneck translate API call, plan and reason exclusively in ASCII, and then output. A strict dose-response ablation test confirms this. Removing the translate tool from the model's alphabet lowers cross-lingual agreement in direct proportion to how heavily that model relies on the pivot. Furthermore, this pivot is highly prompt-resistant. When models are explicitly instructed to reason and plan in the native task language, they refuse the instruction on over 99% of rollouts. For production environments, the reality is stark. You cannot prompt a model out of its English pivot. You can only alter its available tool alphabet. As evaluators, we must implement trace parity release gates natively into our pipelines. Evaluating the destination is useless when your actual production risks, latency, and costs live entirely in the journey.